Welcome back, everybody. Special sixth period edition of the video. So again, we're going to be talking about properties of radicals for 2 days. Today and tomorrow, day 1, day 2. Now, the weird thing about these sections is that I kind of had to take them from a lot of different places. Like in our book, in the book that we learned out of this year, radicals was only one section, section 9.1. So what we basically did is we took all of that material. It would have been like a 3-day lesson if we would have learned it in where it was. So what we did is we took that lesson and we broke it apart, and we are going to cover reducing radicals, adding radicals, and subtracting radicals, and then we will have a quiz. That quiz will be sometime next week, and then we will be doing multiplying and dividing radicals, and then have a quiz over that. Okay. So there are two more quizzes left, and they are both covered in radicals. Now, go ahead and take a look here. First thing I want you to do, everybody take out your calculators. Okay, we're going to need our calculators today. And so let's just make sure that we have them out and ready to go. So what I would like you guys to do while I'm passing around the guided notes is to take a look at all 4 of those lists and figure out the perfect square in each one of those lists. There is one perfect square in each one of those lists. Identify. Okay, first let's start off by defining what is a perfect square. It's not a decimal when you square root it, right? If you square root it, it is a number that is not a decimal. So which is the perfect square in list 1?
81.
81. What about list 2?
25.
List 3?
256.
Yeah. A lot of people might try to say, just if you had not plugged it in your calculator, might try to say 1,000. 100 is a perfect square, not 1,000. And then in the 4th list?
196.
196. Yeah. Those are all numbers that if I square root them, they come out nice and even, nice and whole numbers if I square root them. Basically, if I inverted it, any number squared would be a perfect square, right? Any number squared would be a perfect square. Like 9 squared, you get 81. 5 squared, you get 25. 256, that would be, that's 14. 16, yeah, 16 squared, 14 squared, okay? Now, so let's talk about what a radical expression is by definition. An expression that contains a radical, this is kind of a silly definition. An expression that contains a radical sign is a radical expression. Right? An expression that contains a radical sign is a radical expression. There are many different types of radical expressions, but in this course, this class, we're only going to be talking about square roots. Basically, if I have a, this invisible 2 written. I know we talked about other radicals where we have rational exponents. Actually, I never asked that question. Were there any 5 to the 2/3 power? Were there any fraction exponents on the state test?
I don't think so.
That's something that only shows up once in a while, and it was only like one time on a state test that was released. I'll have to see when they release the materials. The expression under the radical sign is called the radicand. Okay, that's the fancy word for the thing inside the house, right? That's the fancy word for the thing inside the radical sign, the radicand. Okay. Radicand can contain numbers, variables, or both. It may contain one term or more than one term. Now, remember that 16, the square root of 16 is 4, right? Because if I take the square root of a perfect square, it comes out as a nice whole number. 16 is an example of a perfect square. Now, in my opinion, these you should have memorized. I am not going to test you on it, but I believe that you should have these numbers in your brain. The perfect squares up to 10. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. You should be able to recognize perfect squares up to 10 without any assistance, without any calculator. You should be able to. Back in the day when dinosaurs roamed the earth, when Mr. Laverick was in Algebra 1, my old teacher, shout out Mr. Wriggler. Shout out, if you're watching on the internet anywhere, shout out Mr. Wriggler. He made us, he was an interesting guy. He made us memorize all the way up to 20. We had a timed test. It was a minute. You had to write out all the perfect squares all the way up to 20. Now, I'm not that mean old Mr. Wriggler. I'm not that mean. I'm not going to give you a timed test, but it might be a good idea to see those numbers and be able to start recognizing them. Like, for example, let's see if I can still do this without looking at the chart. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196, which is kind of interesting. Look at those two. The two last numbers are just flip-flopped. 15 squared is 225. 16 squared. Now, interesting. This is where it started to get a little fuzzy, but I have to think about them. If I have 16 squared, it ends in a 6, right? If I take 6 squared, it would be 36, right? So I know 16 also ends in a 6, and that reminds me that it's 256. Like, for example, 17 squared. 7 squared is 49, right? So I know 17 squared ends in a 9. And then it's like, oh, that's right, it's 289. 7 squared is 49.
Oh, okay.
Like 18 squared. What is 8 squared? 64. So I know that 18 squared also ends in a 4. And then that's 324. 19 squared. Well, 9 squared ends in a 1. Ooh, is it 351 or 361?
50.
Oh, is it 60? Darn it. That's the one I always screw up. 361. And then 20 squared is 400.
Oh, cool.
Again, back a long time ago, I had to memorize those. We had our timed test. You had 1 minute, 60 seconds to write out all perfect squares up to 20. I don't think you need to memorize them just because calculators have gotten, there's calculators built in your phone, there's calculators. You don't need to memorize them, but you should be able to recognize them. If you see the number 144, you should know that that is also a perfect square. If you see the number 324, that is also a perfect square. So, what happens when we have numbers that are not perfect squares? What do they come out to be again? Decimals, right? I'm not going to make you plug these in your calculator. But just know that if it's a square root of a non-perfect square, oh, I'm surprised. Did we not write those in?
Oh, yeah.
Okay, I thought we were doing that along with me. I see a lot of people that blank right there. So if you have a non-perfect square and you go to square root it, it'll just be a decimal, right? It'll just be a decimal. Like, for example, I think one of the examples up there was the square root of 432, right? If you square root 432, now you know that it's going to be somewhere around 20, right? Because the square root of 400 is 20. I bet it's like 21 something. Oh, 20.8. A little less than I thought. 20.8. Just try to remember that whenever you take the square, we're going to get deep into reducing radicals. Whenever you take the square root, try to remind yourself that it is just a number. It's just a number. It's just a value. Okay? So, let's take a look here. This is your first example down there. I want to simplify the square root of 60. Now, when I say to simplify a radical or to put something in what's called simplest radical form, what I am asking you to do is not give me a decimal, but give me the most exact answer. Like, for example, if I was looking at the square root of 60, I can kind of estimate it based on I've got 64 right above it, right? And 64, if I square root 64, I get 8. The next biggest perfect square would have been 49. That was 7, right? So I know that the square root of 60 is some number between 7 and 8. Closer to 8 than it is to 7. Maybe like 7.7 or something like that. But the problem with this is if I go to square root 60, that is even a rounded answer, isn't it? This is a non-repeating, non-terminating decimal. It is an irrational number. So technically, 7.745966692, blah, 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 that's not going to be exact. So to make it exact, to make it exactly non-rounded, what we're going to be doing is putting things in simplest radical form. Now, I'm going to teach you a method of doing simplest radical form. There are other methods. I will talk about some of the other methods tomorrow, but today we're going to stick with the method of what's called using factor trees. Okay, factor trees. Now, you've been doing factor trees since you were in elementary school. Basically, a factor tree is just dividing that number, dividing it until you get its prime factorization. For example, what number could I divide 60 by pretty easily? 2 and 30, right? Yeah, I can divide it by 2. Is 2 prime?
Yeah.
Yeah, like if I can't split 2 up anymore, right? That's how I know I've gotten to the end of that one. Okay, break up 30.
10 and 3.
I like to keep doing 2s, 2 and 15.
Wow.
Could I have broken it up into 10 and 3?
Yeah.
Sure, that would be fine. I like to keep doing 2s until I can't anymore. Like 15, I can't divide that by 2. But I can divide that by 3. That's 3 and 5. But no matter what, I get the prime factorization. Look down here at all of the end numbers, 2, 2, 3, 5. So that is essentially, if I wanted to rewrite it, 2 times 2 times 3 times 5. You follow me there? If I would have put 2 times 2 times 3 times 5 in my calculator, what would I get? 60. And all I did is just rewrite it in terms of its prime factors. Now, how does that help us with the square roots? Well, it's date night in the square root house, and you got to have a date to leave the house. Who's got a date? 2 has a date. 2's got a date. It can leave the house. That was like quick. Tom's got a date. So 2 gets to leave the house. And when you leave the house, 2 become 1. They join together and become one single unit on the outside. A 2. And then on the inside, what's still there on the inside? The 3 and the 5, right? The 3 and the 5 didn't have buddies to come outside the house, so they got to stay inside the house. Okay, so 3 and 5, they can go back together to make 15, though. 2 radical 15 is my answer. That is what's called simplest radical form. Now, just as a reminder, did I change the value of the number? No. I just put it into what's called simplest radical form. Like if I took the square root of 60, duh, I already did that. I did that right above it. 7.745. Now, if I recalculate 2 radical 15, what should this come out to be?
Same number.
The exact same number. So you can check your answers in the end by going back to the original number, putting that into your calculator, put your answer into your calculator. It should be the exact same thing. Let's do that again. Square root of 72. Again, I like to keep dividing by 2. 2 and 36. And 36 is 2 and 18. And 18 is 2 and 9. And 9 is 3 and 3. So there's my factor tree for 72. Let's write it as its prime factorization. Okay, we've got 1, 2, 3 2s and 2 3s.
This will be interesting.
Okay, now we have 2 sets of buddies, right? Doing the buddy system.
What about? Can't 3 of them
It's
go out on? Like,
Now, but buddies, not 3s, buddies. Now the 2 and the 3 gets to come out, right? I've got a 2 coming out. I've got a 3 coming out. 2 and a 3 on the outside. And then we got our lonely 2. Has to stay in the house. So 2 times 3 on the outside gets us a 6. And then we have radical 2.
Too bad for that too, man.
I know.
You could have got with the other two, you know.
Yeah, but it's buddies.
It's buddy smash.
But you could have picked. Couldn't you have picked the twos before? Like.
Could I have? Yeah.
And then.
Yeah.
It's just yeah.
His buddy smash.
He's just unlucky.
Yeah, just on
His buddy smash.
Maybe he offended the other 2 and he didn't want to.
Yeah.
All right, take a look at another one here. Now, what happens when there's a number out front? We got 2 radical 675. Okay, here's what I do. That 2 is going to stay on the outside and have to calculate back in. So I always like to keep it on the outside. I like to put an equal sign 2 right out there so I don't forget about it. Now, 675, that can't divide by 2, but it can divide by 5, right? Pretty easily. If it ends in a 5 or 0, I can divide by 5. So I'm going to take 675 and divide that by 5, and that's going to give me 135, which in itself can still divide by 5 because it still has a 5 on the end. So 5 and 27. Now that one I can see. That's 3 times 9. Right? That's not that can't be divided by 2, but it can be divided by 3. And then 9 can be divided up into 3 and 3.
Ooh.
So our prime factorization is, I like to keep them in order, 3 3s and 2 5s. Okay, so buddy system. I got a 3 and a 5 leaving the house. Okay, so let's bring them on the outside. Don't forget about the 2 that was already out there. And then I've got a lonely 3 staying in. Now, 2 times 3 times 5. 2 times 3 is 6, times 5 is 30. 30 radical 3. Now, if you were second guessing your answer, if you were like, I don't know if that's right, go back to the original. That was 2 square root 675. And then I've got 30 square root of 3. Oops. Oh, sorry. 2 radical 675. And then 30 square root of 3. Same number, right? That should always happen. Try the next one.
What if you get like 2 perfect couples without anything inside of the house?
Well, then there's nothing left over. Nothing. No more house.
Oh, so you gotta knock down the house because nobody's living in it.
Sure. Shh. Get to work. That means that number that was inside the house was a perfect square. You just didn't recognize it at the beginning. Does that make sense? Come on, get to work, please. Now, it doesn't matter how you break down 96. We had some discussion going on earlier today, and they were like, well, I did this, and I did this, and I did this. And I said, doesn't matter. It doesn't matter how you break it down. It doesn't matter how you break it down, just as long as you break it down correctly. So, like, for example, 96. I'm going to take 96. I'm going to divide that by, I like to divide by 2s. And I get 48. I'm going to divide that by 2, and that's 24. I'm going to divide that by 2 and 12. Divide that by 2 and 6, which gets me 2 and 3. So in the end, I've got that 3 sitting on the outside. And on the inside, I've got 1, 2, 3, 4, 5 2s and a 3. 1, 2, 3, 4, 5 2s and a 3. So let's buddy up. How many 2s are coming out? 2 2s are coming out. Yeah, remember 2 become 1.
Oh, yeah.
Oh.
So 3 already on the outside from the original problem. And we got 2 2s coming out. Guys, cut it out, please. And then a 2 times 3 is 6 on the inside. So 3 times 2 times 2 is a 12. Radical 6. Yes, Don. Good question. Yeah, you can do that. And we'll talk about what to do with exponents here in a minute. Now, be careful. Is 4 prime? No. 4 can still be broken apart. So if there was just 1 4, you would have screwed up. Because there was a buddy of 4, because there were 2 sets of 4s that came out, then that worked. But that's a unique case like that. Does that make sense?
So why do you have 2 2s instead of like 2 instead of 3 in the
3 on the outside and 3 on the inside.
yeah.
You can only buddy up things inside the house together.
Okay.
That 3 has already had its buddy and is already out. Yeah. All right, let's keep it going now. So how do we work with powers? How do we work with variables? That's what we're going to look at next. Because we learned earlier on that a radicand can be letters or numbers or both. So let's figure out how we work with variables. Okay, think about x squared. In terms of its prime factorization, isn't that just x times x?
Right. Yeah.
Buddy system.
Of course.
So what does that become? Just 1x coming out. Remember, 2 become 1. Just an x on the outside. Is there anything left over?
Not a bit.
So therefore, it's just x, or x to the first power, if you will. Let's take a look at x to the third. Okay. I've got 1 set of buddies coming out and 1 staying in. Let's take a look at 4 and 5. Well, for 4, let me change colors here. I got 2 sets of buddies coming out. So what does that turn out to be on the outside? X squared, not 2x. X squared, because I would have an x times an x sitting on the outside. So x squared. Let's look at x to the 5th. Okay, so we have two buddies coming out, but now 1 staying in. Now, I'm going to do 6 and 7 as well. So if I've got x to the 6th, 1, 2, 3, 4, 5, 6. I've got 1, 2, 3 sets coming out. Logan, go sit up there. Go away. Because Chance can't handle himself, you can't handle yourself. Just go sit over there. So we have x to the 3rd. Now, x to the 7th. 1, 2, 3, 4, 5, 6, 7. I've got 3 buddies and 1 staying in. Look down at your papers. Do you see a pattern? Raise your hand if you see a pattern. Chase, what's my pattern?
Odd numbers have 1 in the house.
Good. odd numbers, odd powers, right? Odd powers have one left over in the house. What about even powers? Do they have one left over? No. What's another pattern that we notice?
It's just going up by one. What's it like?
Yeah, but how does it relate to where we started?
For every two, like, I don't know. For every two, you add a power.
Kind of.
It goes like x squared plus one.
Mm-hmm. What about all the even powers? Notice something in the even powers. Without even writing it out, what is the square root of x to the 8th? X to the 4th. What did I do to the power? Divide by 2. So if I asked you x to the 54th, what would that equal? X to the 27th.
Oh.
Thanks. I thought we could divide by 2. X to the 27th. You see how that would work? You can divide by 2. Now, how do you get the power if it's odd then? Well, think about it this way. If I've got x to the 25th inside, you know because this is odd, it's going to look like this. But what's the power on the outside?
Well, you just like minus one and then
You just minus 1 and then divide it, right? So what's that going to turn into? 24, because that's this one.
12.
So 12. It would have 12 buddies. Now, could you fall back? Could you fall back and do just writing it out every single time? Yeah, but if it's a big power like that, are you going to spend the time writing it out? No. So again, for the odd powers, all you need to do is subtract 1 from the exponent and then divide by 2. That's the power on the outside. Then make sure you just tack that on. Now, here's the example you have on your page, even though it didn't come out right.
Wow.
Can you write that in there, fill in? It kind of got a little pixelated there. Didn't copyright. Square root of x to the 4th, y to the 8th, z to the 3rd.
I don't know.
Well, is the power on x even?
Yeah.
Yeah, so just divide by 2. X to the 2nd. Is the power on y even?
Yeah.
Divide by 2. Is the power on z even? No. So we know we're going to have a radical z in there. And then I would knock it down 1. So z to the 2nd. And then I would divide by 2. So 2 divided by 2 is 1. So just z. Or z to the 1st. Again, if it's odd, you subtract 1 from the power, then divide by 2. Now, could I have written it all out? Could I have said 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3? Of course I could. I've got 2 buddies with my x's, 1, 2, 3, 4 buddies with my y's, a buddy with my z, and a z staying in. Totally fine. Okay, let's do some more examples. 50x squared y to the 3rd. So now I've got numbers and variables going on.
Scary.
Question.
I have like a test or a quiz. Would you require us to like show work on how we got like our answers?
Always.
It's math. No, well, like can we just like do it like
For the variables?
Yeah, like if we had y.
Yeah, I mean the variables are fine, but don't do that with the numbers. Just be careful if you didn't show any work and got it wrong. No partial credit. All right, 50x squared y to the 3rd. Let's break it apart and just do each piece separately. Let's do the 50. Okay, that's 2 and 25, 5 and 5. Now, everybody look up here real quick. Just look up here real quick. You know, back on the front, I had written it out on this step using the prime factorization, right? I get a little lazy. You know what I usually do? Is I look at it from here and I say, oh, I've got a set of buddies right there. And then you could look at it from there and say like, oh, I don't need to write it all out again. What's going to be on the outside? A 5 coming out. What's staying in? A 2. Now I'm going to leave a little room because I know I got some variables in there. 5 coming out, 2 staying in. Right? Now, what's coming out for my x's? Just an x. And then a y, still just a y, and then what? A y inside because it was odd. 5xy radical 2y. That is what's called simplified as a radical. Let's take a look at the second one up here. 160 a to the 4th b squared. Okay, let's break down 160. Let's break down 160. That's 2 and 80, 2 and 40, 2 and 20, 2 and 10, 2 and 5. Could I have broken this apart differently? Sure, but you should still get to the same prime factorization. So let's buddy up. Looks like I've got 2 set of 2s. What's that make on the outside all said and done? 4. And then on the inside, I got a 2 and a 5. A 10. Okay, now, I guess I didn't even need to leave a little room inside my radical because these are both even powers. Just divide by 2. A squared, b. And now we'll do our last one here. Now, be careful. You know what the most common mistake is that I see all the time? Forgetting the 5. So that's why I say equals 5 times something. Remind yourself about that 5. Write it out there because you will forget it if you don't write it out there. 504 can be 2 times 252, which is 2 times 126. I'm good there. 2 times 63. I know that's 7 times 9, right? And then 3 and 3.
Wow.
You could have said 3 times 27. That would have worked too. I just recognized 63 was 7 times 9. All right, let's buddy up. Buddies. Buddies. Okay. So I've got a 2 and a 3 coming out. What does that make? 6. Okay, staying in, what do I have? 14. I had a 2 and a 7 staying in. Now, the x just comes out. The y stays in. So all said and done, 30x radical 14y.
Wait a minute. Well, I got a question.
What's your question?
So how did you get 6 and not like 9 with that?
2 times 3.
You just simplified it.
Right? I knew a 2 and a 3 were coming out.
Okay.
So 2 times 3 got us to be 6.
Okay. Oh, yep.
And then we don't forget about the 5 that was out there, which got us all the way up to 30. Questions about that?
No.
Okay. I'd like us to get to work on our homework. Yeah, we still got plenty of time. We got 10 minutes. So you should be able to get this done. Well, not should be able to get it done, but you should be able to at least get a good head start on it. I want to see factor trees for all these problems.
Yes, sir. Okay. Oh, this is easy. Oh, yeah. So,